I'm Alex Han, the presenter of this paper, Ultrasound Variational Style Transfer to Generate Images Beyond the Observed Domain. So what are some major challenges in medical image analysis, or like ultrasound more specifically? So images taken by different machines or in different parameter settings look very different. So the image distribution would be entirely different. So neural networks trained on one data set might completely fail on another data set. In another word, the generalizability of deep networks on medical images are kind of poor. On the other hand, labeling, especially for medical data, is like really time consuming and then requires expert knowledge. So more often than not, we would not have really big data sets. Our paper intends to solve such problems, at least some of the problems. The first of the main contribution of this work is that our method is the first variational style transfer approach that explicitly samples style from a latent space without giving the network a style reference image. The second contribution is that the approach can be used to do data augmentation, and we have shown that it helps to improve segmentation results, which we will show later in the experiment. The third contribution is that by this method, we can transform the image into some style that's not seen before during training. So here is an overview of the method. We use a UNet as the backbone, but it should work with like any encoder decoder framework as the backbone. Anyways, the network consists of three parts: a content encoder EC, which is just like a normal UNet, which is this part, and a style encoder, this part ES, and also a decoder. And the style encoder is actually just a UNet encoder that learns a Gaussian distribution at different scale, and the decoder takes in the style and content deep features and perform an adaptive instance normalization. To go into more details, the style encoder learns a distribution QZ given I to approximate the true distribution PZ given I, which is intractable. The variational lower bound can be expressed by this equation 1. And in this way, we learn the distribution of the style that we can sample from. As for the decoder, it takes in the style features FS and the content features FC. And then we use adaptive instance normalization added in to merge the two features and then output this F hat as it's shown in this equation 2. After that, we treat the F hat as the skip connection feature from like a normal UNet. Okay, so in terms of the loss function, the goal of this work is to generate an output image that contains the content and content images and the style from the style images while maximizing the variational lower bound to learn the correct distribution. Therefore, we divide the loss function into 3 parts. Perceptual loss between the output and the content images, the style loss between the output and the styled image, and the KL divergence between the learned distribution and a normal distribution. So please take a look at our paper for more details. So the data set we were using for this work is a combination of the 8 data sets listed here. During training, we randomly sampled a pair of images as the content and styled images without like any other restriction. So here are some qualitative results. The result on the left is the result of transferring the style from between like those 8 data sets with our method. And these are the styles images. These are the style images, like the first row, and these are the content images, like the first column. And we can see that the generated images have the content of the content images while having like the brightness, textures, and stuff like that of the style image. However, if we do the same set of experiments with the previous style transfer approach, the result doesn't look as good as some of doesn't look as good because some of them have like really weird stuff going on the images. The result on the right is from the previous approach. We can compare it against the last row of the image on the left, because the input and style images are the same. And we can clearly see that our method works better than the previous one. Okay, so in this experiment, like we visualize the latent space of the style and have the figure here on the left. I mean, that's the visualization of the latent space. And we have the one on the right where that's like the sampling result of the style from the latent space. And on the figure, on the left figure, like each color represent different style. So we can see that most of the points from the same style are kind of in the same cluster. And so like I said, we then sample like 4 pairs of random points in the latent space and interpolate between each pair. The result is this one on the right. So like some of the results are clearly like not the style that were seen during like training. So that's pretty good. Okay, so at last, this is some quantitative results. And the quantitative experiments that can show that our method can improve the performance of segmentation. Assume that we only have limited live pick data while having a lot more phantom data. Denote our variational approach as VT, deterministic approach as DT, and traditional augmentation as log. So PH in the table means phantom data, and pig means pig data. The number after the pig data indicates like how many pig images were included during training. For example, the first line in the table, like this line, indicates we use variationally transferred phantom images along with 99 pig images and have the traditional augmentation on top of that. For fair comparison, we use a traditional UNet for segmentation under the same training setting as the original paper. The results in the table can show that almost all the best segmentation results use our variationally styled transferred images. So thanks for listening, and here are some references. For more details, please, again, refer to our paper. Thank you. How do I stop this?